this model we are going to discuss limiting distributions. So, we cover three important topics. First topic is called modes of convergence, and the second topic we are going to discuss law of large numbers, and the third topic which we are going to discuss, that is a very important topic, that is central limit theorem. In this model we are going to discuss these three topics as three different lectures. In the first lecture we are going to discuss modes of convergence. Second lecture we are going to discuss law of large numbers. Third lecture we are going to discuss central limit theorem. The first lecture is on modes of convergence. Till now what we discussed, the probability space, probability of an event, then we discuss a conditional probability of events, then we have introduced a random variable, then we discuss the CDF of the random variable, then based on the discrete type or continuous type random variable we discuss the probability mass function, probability density function. After we introduce one random variable in a probability space, we have discussed the distribution in the form of a CDF, density function or mass function. Later we said one random variable is not enough to solve some particular problems. You may need more than one random variables to be defined in the same probability space to solve the given problem. Then we introduce two random variables, then we discuss the CDF, we discuss the joint probability mass function, we discuss joint probability density function, then later we discuss the conditional probability density function, conditional probability mass function. For the first random variable we discuss the mean, variance and so on, that I missed it earlier, second order moment, nth order moment and so on. And here we discuss the conditional distribution, conditional probability, conditional expectation and so on. Not only two random variables, then later we introduce n random variables in the same probability space. Then we discuss the joint distribution of n dimensional random variable. After that we introduce the transformation from one dimensional to another n dimensional random variable or r dimensional random variable and so on. Now we are going to discuss not a one random variable, not two random variables, not n finite random variables. We are going to discuss a sequence of random variables. This is also possible when you solve a given problem. You may need to know the sequence of random variable and what is the distribution as n tends to infinity. The first question comes whether if you have a sequence of random variables, whether this sequence of random variable converge or not, converges to one random variable or not. If it converge, what is the distribution of that sequence of random variable? That is going to be the topic of modes of convergence for the random variables. For this, first we can understand how the sequence of real numbers converges. Suppose you have a real numbers a1, a2 and so on, an and so on. Whether this sequence of real numbers converges or not. If it is converges, that means an converges to say a. What is the value of a? That we have discussed in any real analysis courses of a sequence and a series of real numbers and so on. The same concept we are planning to introduce for the sequence of random variables, but the only difference is the random variable takes real numbers with some distribution. That means the x1 random variable can take the real values x1 with some distribution. Similarly, the random variable x2 may takes the values, real values x2 with some distribution and so on. Similarly, the random variable xn can take the real number xn with some distribution. If you know the distribution of each random variable x1, x2 and so on, you have a sequence of random variable, all are defined in the same probability space. That is very important. All are defined in the same probability space, and if you know the distribution of this sequence of random variables, whether this sequence of random variable converges to one random variable or not. If it converges, what is the distribution of that? That means if I write xn converges to x, this is a notation. When I write xn converges to x, that means I have a sequence of random variable x1, x2, x3 and so on. Whether this sequence of random variable converges to the one random variable, that is called it as x. If I know the distribution of xi's, what could be the distribution of x? That's the question. In sequence of real numbers converges to one real number a, that may be easy comparing to the sequence of random variable converges to the one random variable. Since each random variable attached to it some distribution, for some random variables moments of first order may exist, further moments may not exist and so on. Therefore, you cannot make only one way you can conclude that this sequence of random variable converges to one random variable x. There may be more than one ways you can conclude that this sequence of random variable converges to one random variable. That we call it as a modes of convergence. So, we are going to discuss there are four modes of convergence. The first mode of convergence we write it as xn converges to x in distribution by writing small letter d above the arrow. I am going to give the definition one by one in detail with examples. Comparing to the sequence of real numbers, how it converges to one random variable. Similarly, we are going to discuss how the sequence of random variable converges to one random variable in different ways. The different ways we say it as a different modes. The first mode of convergence, that is called the convergence in distribution with the letter small d above the arrow. The second one, that is a convergence in probability. The third one, convergence in orth moment. The fourth one, convergence in almost surely a dot s. Above the arrow, if you write d, that means convergence in distribution. Above the arrow, if I write small p, that means convergence in probability. Above the arrow, I put a slash with r, that means it is a convergence in the orth moment. The fourth one, convergence in almost surely. So these are all the four ways the sequence of random variable defined in the same probability space converges to one random variable which we denoted as a capital X, that is also defined in the same probability space in four different modes of convergence. Let us start with the first mode of convergence, that is convergence in distribution. In distribution, let x1, x2 and so on, xn and so on be a sequence of random variables with CDF F1, F2 and so on, Fn respectively. That means the random variable x1 has a CDF F1, the random variable x2 has a CDF F2 and so on. All these random variables defined in the same probability space. We say that xn, the sequence n, take the value 1, 2 and so on, converges in distribution to the random variable denoted by capital X can be written as xn converges to x in distribution if limit n tends to infinity fn of x, that is same as f of x for all x where f is the CDF of the random variable x. As long as the limit n tends to infinity, fn of x is same as f of x, where f of x is the CDF of the random variable x, that is valid for all x. This condition is valid for all x. Then we can conclude the sequence of random variables convergence in distribution to the random variable x. Note that f1, f2, fn and so on, that is the CDF of the sequence of random variables respectively, and that converges to a function that is the CDF of the random variable x. Then we can conclude this convergence in distribution to the random variable x. Let's give one simple example. Through that we can understand the definition clearly. Example: let omega f capital P be a probability space let xn, n is equal to 1, 2 and so on be a sequence of variables defined on the probability space omega fp, that is defined as xn is defined from omega to r such that x n of w that is equal to 1 by n for n is equal to 1, 2 and so on. So, we are defining the sequence of random variable from omega to r such that x n of w takes a value 1 by n for n is equal to 1, 2 and so on. Now, we will find out what is the CDF of this sequence of random variable. So, if you find out the CDF of the nth random variable as a function of x, this is going to take the value 0 when x is going to be lesser than 1 by n. From 1 by n onwards, when x is going to be 1 by n onwards, it is going to take the value 1. So, this is going to be the CDF of the sequence of random variable xi's. So, here n takes a value 1, 2 and so on. Now, let us go for finding the limit n tends to infinity of fn of x. What could be the value as limit n tends to infinity for the fn of x? This is going to be 0 when x is lesser than 0, because as n tends to infinity of 1 by n, that becomes 0, and 1 from 0 onwards. This is a limit n tends to infinity of fn of x. Suppose I denote this as the f of x. Suppose I make f of x that takes a value 0 when x is lesser than 0, 1 from 0 onwards. Verify whether this is going to be the CDF of some random variable. It starts from 0, land up 1 and so on. It satisfies all the properties of a CDF. Therefore, this is the f of x is the CDF of some random variable. You denote it as a capital X. Say f of x is the CDF of the some random variable x. By seeing limit n tends to infinity of fn of x, that is same as f of x. Since limit n tends to infinity fn of x, that is same as f of x, where f of x is the CDF of some random variable x, and the left hand side fn of x is the CDF of the sequence of random variable, or fn of x is the CDF of the random variable xn. As the limit n tends to infinity, that is same as the CDF of the random variable x. Therefore, we can conclude this is a condition is satisfied by the convergence in distribution. Therefore, we can conclude x n converges to x in distribution. There is a possibility the sequence of random variable CDFs may converge to some function that may not be the CDF. So, as long as this sequence of CDFs converges to some function that is also the CDF of some random variable, then you can conclude the xn converges to x in distribution. So like that we have some more problems that we will discuss little later. That means when we discuss other mode of convergence, we can verify whether this satisfies the convergence in distribution also. So now we will move into next mode of convergence, that is convergence in probability. Let x1, x2, xn and so on be a sequence of random variables defined on the probability space omega f p. We say that this sequence of random variable converges in probability to the random variable capital X, and write it as xn converges to x in probability if for any epsilon which is greater than 0, limit n tends to infinity, the probability of absolute of xn minus x greater than epsilon, that is equal to 0. If this condition is satisfied for any epsilon greater than 0, finding out the probability in absolute sense xn minus x greater than epsilon, limit n tends to infinity is going to be 0, then we conclude that this sequence of random variable converges in probability to the random variable x. Note that to verify this sequence of random variable converges in probability, you should know the random variable x, then finding out the probability. After this verified, then you can conclude this sequence of random variable converges in probability. That means you should know about the distribution of the random variable x, or at least you should know how to compute the probability of absolute of xn minus x greater than epsilon for any epsilon greater than 0. That means beforehand you should have the distribution of the random variable x along with the distribution of the sequence of random variable xn's, then only you can conclude whether this sequence of random variable converges in probability. So for this mode of convergence, we will go for the example. Through that we will understand. The example is example, let xn be a sequence of random variables defined on omega f capital P such that the probability of xn is equal to 0, that is 1 minus 1 divided by n, and the probability of xn takes a value n, it is 1 divided by n. So this is true for all n is equal to 1, 2 and so on. We have a sequence of random variable whose distribution is defined xn takes a value 0 with the probability 1 minus 1 by n, or xn takes a value n with the probability 1 by n. That means this sequence of random variables are of the discrete type, which has the 2 points 0 and n are the mass points. Either the mass is at 0 or n for the nth random variable, and you have a sequence of random variable n is equal to 1, 2 and so on. In this example, we can go for taking let epsilon greater than 0, you can go for finding probability of absolute of xn which is greater than epsilon, finding out the probability of absolute of xn greater than epsilon. That is same as this is going to be 1 by n if epsilon is going to be lesser than n. If epsilon is going to be greater than or equal to n, the probability of absolute of xn greater than epsilon is 0. This is for fixed epsilon is greater than 0. Now we can go for taking a limit n tends to infinity of a probability of absolute of xn greater than epsilon. As limit n tends to infinity, this quantity is going to be, the right hand side is going to be 0. Since the limit n tends to infinity, probability of absolute of xn greater than epsilon is 0, therefore you can treat the absolute of xn minus 0, that is equivalent of concluding xn converges to 0 in probability. 0 you can treat it as the a random variable x takes a value 0 with the probability 1. You can make xn tends to x in probability, where x is a degenerate random variable or constant which takes a value 0 with the probability 1. So sometimes the sequence of random variable converges to constant also. So this is an example in which we have given sequence of random variable converges to constant 0 in probability. Since it is a converges to 0, therefore we are directly going for a probability of absolute of xn greater than epsilon. Sometimes if you have a random variable x and whose distribution is known, then you can go for finding out the probability of absolute of xn minus x greater than epsilon. Then whether the limit n tends to infinity, this quantity is going to be 0 or not. Accordingly, you can conclude sequence of random variable converges to random variable x in probability or not. So here it is a very easiest example in which we are land up a sequence of random variable converges to 0 in probability.